welcome to today's lecture. We will continue our discussion exactly from where we left in the last class. We were discussing about the some of the practical tips, some of the clues to do microthermometric experiments on our judgment of choosing the inclusions and not introducing much of mistakes in the choice of the inclusion. And in such kind of heating experiments, we are generally fraught with this we generally face this problem that sometimes inclusions are overheated, and if those inclusions overheated beyond the temperature of their homogenization, that means the point at which they attain the homogeneous state, and we know that any further heating would actually make the inclusion move on the isochore, and if the inclusion is dense, contains higher weight percent NaCl equivalent, it will follow a steeper isochore, and there will be lots of higher internal pressure generated on the wall of the inclusion on the host crystal, and the inclusion leaks. So, if we see this, what we have been discussing, we were just trying to understand that if an inclusion which is overheated beyond its temperature of homogenization, if we are observing it and we are going beyond the temperature of homogenization, and while observing the inclusion the leakage takes place, then we will be able to very easily detect that change during the microthermometric experiment. So, we know that this particular inclusion has leaked during microthermometry, but there are chances that the inclusion might have leaked because of some earlier episode, some thermal perturbation even during the process of its evolution, or there are chances that during a microthermometric experiments on an inclusion which we are not observing, but a nearby inclusion in the same sample which is has a little different kind of a composition, or the was trapped at a different temperature pressure condition, it might so happen, or the inclusion is larger, either of these possibilities, the inclusion would have leaked. So, if the inclusion leaks, then there is the content of the. So, it is exactly the process, the as and when the inclusion leaks, a part of the content gets out of the main bulk of the inclusion and gets immediately sealed. So, actually the process is exactly similar to a sealing process, or to entrapment or encapsulation process that takes place primarily in the mineral that is growing from the fluid. So, that means if this inclusion is leaked and then again has it is almost like as if a fresh sealing has been a fresh entrapment actually has taken place at a higher temperature, and that will explain why the vapor bubble will be larger compared to what was there in the original inclusion. And we know that we did not see, or we did not measure, we did not have any idea about what exactly it was. If it happens to be an inclusion which we have taken a freezing run initially, and we noted down the appearance, or even taken a sketch or a photograph, and then we are by in the course of changing to a heating experiment, then we are heating this particular one, and we find that the vapor bubble seems to have sort of grown larger than what it was before, or we could clearly see some satellite inclusions like this in this case or this case around that inclusion, that we know that this inclusion has been leaked. So, the suggestion is that it is better not to take the run of this particular inclusion normally. And also in this I would also like to mention that the heating freezing experiments is done in such a way that we put the chip inside the equipment, inside the heating freezing system. The photograph, the image which we have shown, each of these heating freezing system will have a sample chamber where a particular chip which is broken from the fluid inclusion section is put inside that sample holder, and when we do a freezing study, we first do the freezing study on all the aqueous biphase inclusions that are there, that we plan to take the freezing runs. It is not that we alternately heat, even though in a stage like a Lincoln THMS G600 kind of a stage, it is possible that the same inclusion could possibly be frozen and then again heated, but I would suggest that a freezing study, a freezing run should be first completed on all the inclusions that we plan to take, and then this gives us it becomes sometimes the practical problem is here that to relocate back those same inclusions on which freezing runs have been taken, because as we will see that our data on these inclusions have to be paired data on their homogenization temperature and the salinity in terms of weight percent NaCl equivalent. So, it is mandatory that freezing and heating run be taken on the same inclusions. So, if we have taken the freezing run on say 10 number of inclusions that are present in a chip, and we decide that we will be freezing these 10 inclusions, aqueous biphase inclusions, then sequentially again we have to relocate them one by one. So, now so in that process, if any particular inclusion would have been overheated, then it should be very well documented and the data of that particular inclusion should be discarded. Okay. There could be many more such kind of practical aspects of fluid inclusion studies, and as in we may discuss some of them as in when they come, even through case studies. So, we will now from the aqueous biphase inclusions, we will discuss on the other important type of inclusions that we mostly encounter are the inclusions which are the aqueous polyphase inclusion. And the aqueous polyphase inclusions, just to give a little bit of an idea, that considering only the ones where we get a single crystal, that is a sodium chloride, and we have also discussed that there is a possibility that the crystal that we are observing, a crystal of sodium chloride, is that it is precipitated from the liquid as the temperature pressure conditions decreased. There is another possibility that this particular salt crystal is not a result of precipitation from the liquid on attainment of saturation, but it is actually a case of heterogeneous entrapment or caught up as a solid phase when the inclusion was trapped. Now, since this stage we are only considering homogeneous entrapment, so we will not consider those cases now, and in such cases where, so the only way to, so when we are doing experiments on such kind of polyphase inclusion, it is good to actually keep it in mind that when we see aqueous polyphase inclusions containing halide daughter crystal, it is very possible that we should get a group of such inclusions, polyphase inclusions in a sample, rather than just a stray case of only one, a lone inclusion containing a halide daughter crystal and no other such polyphase inclusion that are observed in the sample. Then it gives us our suspicion that it possibly could be instead of being a daughter phase, it could be a captive phase, captive daughter crystal which is caught up as a process of heterogeneous entrapment. So, we go by the assumption that the entrapment was homogeneous and the daughter crystal which is observed in the inclusion cavity is a result of precipitation as a post entrapment phase change, precipitation from the liquid on attainment of saturation with respect to that particular solid crystal, and in this case it is sodium chloride. And we and also we discussed that such inclusions, the freezing study of such inclusions is not going to give us any idea on the salinity of such kind of inclusion. So, the basic idea is that we want to get the salinity of this inclusion to calculate density. So, now we will talk about the microthermometry of the halide bearing aqueous inclusions, and let us take the case 1. So, the case 1, it indicates that okay, this star corresponding to some pressure temperature value, let us say P1 T1, here the one phase liquid, homogeneous liquid was entrapped, and since it is homogeneous one phase liquid, so it will also, as per our own assumption, it will follow a isochoric path, but it will follow an isochoric path till the point where this halide will attain saturation, means there will be appearance of one small nuclei of a halide crystal here. Now, since so this particular the appearance of halide crystal actually would correspond to what is been plotted here as the liquidus, halide liquidus, where it will be halide plus liquid on this side and the one phase liquid on the other side. So, such liquidus, so this liquidus actually correspond to a very fixed weight percent of sodium chloride, as you will be seeing them at what could be the value. So, suppose this is P2T2 temperature pressure corresponding to the point at which the halide crystal has appeared. So, now it will be following a path in the halide plus liquid line, halide plus liquid coexistence. It will be a not exactly a line, would be curve, because the density is going to change. It is not going to be a straight line, but it is going to be a curve. So, it will keep on evolving with the size of the halide crystal gradually growing, and it will finally intersect the curve, which actually is the halide plus liquid plus vapor and liquid plus vapor curve, as we saw before in a phase diagram where water plus NaCl system was depicted with the continuous critical curve, then the halide plus liquid plus vapor curve. So, it actually will be present some will intersect that halide liquid vapor coexistence curve here, and from that point here the vapor phase will nucleate, as in when it comes to the point here there will be vapor phase, and the vapor phase nucleates and the vapor phase goes on increasing in its size. So, this we see at the room temperature, biphase aqueous polyphase containing a vapor plus a sodium chloride crystal. So, this is a situation corresponding to case 1. Now, what is the exactly the same situation what we did before, that we try to reverse this phenomena and record the changes, the phase, and then what kind of phase changes we will be expecting here. So, if we reverse this, so when we increase the temperature, at some point the vapor phase is going to disappear, the liquid vapor homogenization will take place, and then from that we will only have a liquid plus halide which will exist, and it will follow the curve again, and will go on up to the point at which the halide will disappear. So, we will in fact be noting down these parameters. This is of course a temperature of homogenization. We can say that we will get a value corresponding to a L plus V to L, but that temperature will be not of much help to us here, because we have not attained the homogeneous state of the inclusion fluid. We will be attaining the homogeneous state of the inclusion fluid only at temperature pressure corresponding to this P2T2, where the salt crystal will disappear. Exactly the same mechanism, the point at which a salt crystal nucleated, and when we are during the process of heating, when we are reaching at this particular temperature pressure condition, the salt crystal will disappear. So, that will be the temperature of dissolution of NaCl. So, we will represent it in form as Ts NaCl. To be more specific, we can write Ts NaCl, or you can write Ts, and so this temperature Ts NaCl is the one which is the important parameter for us as far as this particular situation is concerned, and here we attain the homogeneous condition, and we know that from this point onwards the fluid will follow an isochore, and the logic is exactly the same we discussed before. We will not be able to reach at a point corresponding to the trapping temperature. We can only go up to a situation where the salt crystal disappears. It is possible to reach at a point of P2 and T2 beyond the temperature at which liquid plus vapor homogenization took place. So, this is the first possibility, and here we are this is the case 1, where the halide bearing inclusions are entrapped and evolve, and the post entrapment phase change takes place, and the heating response which is exactly done to reverse the process, in which we can note down the temperature of liquid vapor homogenization which occur first at a temperature lower temperature, and then further heating it follows a halide plus liquid coexistence curve till the point it meets the halide liquidus, beyond which it is a single phase liquid field and the inclusion has attained homogeneous state and it will follow an isochore. The second case can be depicted as this roughly, that it would have so happened that the inclusion fluid was much less saline, the weight percent NaCl equivalent was less compared to the first case. Here the inclusion is trapped as a single phase liquid, and then on the way of its evolution in the following the isochore, it intersects the liquid plus vapor liquid. So, essentially the boiling curve of the corresponding to that particular liquid, particular water NaCl system. So, it further decrease of the temperature, the vapor bubble grows in size and attains a larger size at particular this point. And again during this process what happens, that the halide attains saturation and comes to existence and we see a halide crystal. So, if we reverse this process, what we expect here, that the temperature of dissolution of halide can be observed between, suppose this is our P, this is the P1 T1, this is P2 T2, this is P3 T3 and this is P4 T4. So, what happens is that this halide which was present in the room temperature will disappear at a temperature corresponding to temperature let us say temperature corresponding to T3. So, further heating from T3 to T2, it is actually follows a liquid vapor equilibrium curve at which T2 the vapor bubble disappears. So, here in fact the temperature T3 is also useful to us, because T3 will essentially correspond to the Ts NaCl. So, here T3 is nothing but our Ts NaCl here, and T2 will be the temperature of homogenization at which the fluid will attain homogeneous condition, and then T1 is the temperature of trapping as we know before. So, here why I say that the T3 is important for us, because T3 is Ts NaCl and the salinity of this particular inclusion fluid is calculated based on this Ts NaCl as before. So, previously the liquid vapor homogenization was not an important parameter to us, but here the temperature T3 which is less than. So, here actually Ts NaCl is less than the Th. So, the previous case the Ts NaCl was greater than Th. So, the homogeneous state was obtained only at Ts NaCl, and here the homogeneous state is obtained in liquid vapor homogenization. So, in both these cases we calculate the density only at which the fluid becomes homogeneous, or the state it attains the homogeneous state, and then we calculate the isochore exactly based on the equations which we have discussed before. If the equations were formulated which will be applicable to a much wider range of temperature and pressure, and also the weight percent of salinity of weight percent NaCl equivalent. So, the equation which we described in terms of the dP by dt being fitted as a function of temperature and salinity, and it has a very wide range of applicability, and most isochores can be constructed. And in case you are dealing with a fluid which is far more saline than, or for the contents the weight percent NaCl content is higher, then the range of applicability of the previous set of equations we can always look for which set of equations should be applicable to construct the isochore in that case. Okay, and the third possibility is the one where the halide. So, here similarly the situation is that the inclusion is entrapped at corresponding conditions of P1 T1 here, so on as the star here, follows the isochore, and it meets at a point which is exactly kind of an intersection of this liquid plus vapor and the halide plus liquid plus vapor. So, here what will happen, that a halide and a vapor will simultaneously nucleate as the temperature and pressure are decreasing, and on further decrease of the temperature and pressure, both the halide and the vapor bubble grow in size, and we see them in this kind of a state at room temperature. So, heating this inclusion will characteristically show that the liquid, that the solid halide crystal and the vapor are disappearing at the same time, and then this becomes homogeneous. And so, here the situation is that Ts NaCl is equal to Th, say we put LV, liquid vapor homogenization. So, there are three situations where Ts NaCl greater than Th. In that case, the density is calculated based on the temperature of Ts NaCl. The Ts NaCl is equal to Th. There also the density is calculated because there the fluid is becoming homogeneous. So, both salinity, salinity is calculated on the base of the Ts NaCl, and here Ts NaCl is less than Th. So, here Ts NaCl is also important for us because the salinity will be calculated based on Ts NaCl, but density will be calculated on the basis of the temperature at which the fluid has become homogeneous. So, these are the three situations which are depicted here. The case 1, there is some little bit of a practicality involved, that what exactly happens. So, if this is the room temperature condition in which the halide is observed with a very well developed faces and the edges. So, with slight increase in temperature from room temperature to say about 100 degree or so, the halide actually dissolves by first rounding off of the edges and becomes a circular in its outline, and gradually decreases in size and becomes almost like a black dot and disappears. So, as compared to a liquid vapor homogenization, here we do not see the halide executing any pseudo Brownian movement because it is a solid crystal, and chances that the similar kind of a situation, that if the inclusion geometry is not very proper and there are some clarity problem, then one may always miss the point of dissolution of the NaCl by a few degrees, but then in that case one has to adopt the same strategy, that go on doing this repetitive measurement of the dissolution of the crystal, and a point here exactly the same thing happens. If one has obtained the temperature of dissolution of halide, say corresponding to Ts NaCl, then decreasing the temperature by a few degrees from Ts NaCl, the halide will not nucleate instantaneously, but will come into existence at a temperature much lower than the Ts NaCl. So, if the this sodium chloride crystal has not fully disappeared or not fully melted or dissolved, then by immediately decreasing the temperature from temperature of the temperature which was erroneously measured as a temperature of a dissolution of halide, the halide crystal will start growing from that particular point. So, these are the practical situations in which by repetitive measurement and some of the inclusions the clarity could be very good, and here also we talk about the reproducibility of the order of plus minus 1 degree Celsius. So, these are the three situations which are discussed. So, in this is Ts NaCl is less than that of Th, here Ts NaCl is more than Th, and here is Ts NaCl is equal to Th. So, we have discussed the issue of are all solids daughter crystals. So, if not, they are captive crystals, and their dissolution will not dissolution temperature is not going to tell much about the fluid characteristics. And the question that do all daughter crystals dissolve, because we discussed that there are polyphase inclusions in many situations where they contain daughter crystals more than one. Sometimes there are a gypsum daughter crystal or a calcite daughter crystal, sometimes there are even sulphide mineral there present as a daughter crystal, and in situations like in porphyry copper deposits there are inclusions with multiple daughter crystals which are reported. We find that the chlorides, mostly the two chlorides are the dominant daughter crystals, sodium chloride and potassium chloride, which is the halite and sylvite. There we find that we are able to obtain the dissolution of the daughter crystal in a heating experiment, but we find sometimes that the kinetics of dissolution in other daughter crystals like calcite or gypsum anhydrate sometimes is very slow, and people report of obtaining such kind of dissolution by doing prolonged heating experiments, keeping the temperature static at a very long time to take care of certain issues, but those are the things which we are not discussing in this particular lecture series, confining ourselves to very commonly encountered situations, simple situations, and which we can use microthermometry for characterization of the fluid and understanding the fluid evolution. Corresponding to the temperature of dissolution of the daughter crystal, which is halite in this case, it also can be fitted into a nonlinear equation in TD for calculation of the weight percent of NaCl. Since we know that the room temperature solubility is around 26.3, so this parameter A mostly will be that, and for the increase in solubility of sodium chloride, that is halite, with temperature can be fitted as a function, a second degree polynomial in TD. And just as we were discussing, we can just quickly have a look on a situation where it is a complex or a ternary sodium chloride, potassium chloride and water system, where there is possibility that we get a situation there are two daughter crystals present, one represented as this green square is a halite, and the one with the orange circular outline is sylvite, that is potassium chloride, and this is what most of the cases it happens. The halite and sylvite, when they are present together, this is the way we see them. Optically they can be distinguished, one having a very sharp faces and edges, one is rounded, which is potassium chloride. So, the heating behavior of such inclusions can be understood with the help of this ternary. This is an H2O, NaCl and KCl ternary part of it, around 60% of NaCl this side, 60% of potassium chloride this side, and we can go, we know that we go from here, this is the pure KCl corner. Now, on this, if we try to use this particular diagram to understand the freezing to the macrothermometric behavior, then here this is the binary, this is the ternary eutectic. The ternary eutectic value is something around minus 23 to minus 24 HCl, NaCl, KCl, minus 24.9 or near about approximately about 25 degrees Celsius, and this is the NaCl H2O, NaCl 2 H2O hydrohalite field, and these are the temperatures. So, this is the temperature contours 100, 150, 200, 250, 300, 400 like that, and let us say that we have a aqueous by aqueous polyphase inclusion containing halite and sylvite as daughter crystals. If we heat them, and also let us presume that this existence of this halite and sylvite have come into been there in the inclusion cavity after the liquid vapor separation. So, the homogeneous fluid, and the first thing to occur here was a vapor phase separation, and with both these halite and sylvite attaining their saturation at temperatures which are lower than the TH. So, here what we see that suppose the bulk composition of the inclusion was somewhere here, which we did not know exactly what it is. We are seeing as halite and sylvite, and say like for example, we start heating it. When we start heating it, this orange circle corresponds to room temperature, where we have the curve which is corresponding to KCl NaCl coexistence. So, both these both NaCl and KCl are present there. If we increase the temperature, because of greater solubility of potassium chloride, this sylvite crystal will first start decreasing in its size. If this, and it will decrease in its size, and by that there will be a little bit of an apparent increase in size of the sodium chloride crystal instantaneously, but that is not going to continue for long. And point corresponding to 2 is where is shown that the halite and sylvite are both existing at a little higher temperature, about 80 degrees, 60 degrees or so, and then temperature at the point 3 about near about 70-80 degrees centigrade or so, the sylvite crystal is disappearing. So, sylvite is completely dissolved, and now it has gone into the region of NaCl plus water stability field, and it will continue to move to the higher temperature in this region with gradual decrease in size of this sodium chloride crystal, and as it happens before this, it will be rounding off of the sodium chloride crystal, and the gradual decrease in size, finally it will just disappear at a point corresponding to 4. At this point, we can, by using the values here on the ternary as we generally read from a ternary diagram, this is 40% NaCl and 15% KCl, which is essentially by the sequences of the changes, the phase changes that we observe in a aqueous polyphase inclusion containing a halite and a sylvite daughter crystal both. So, we are not going on to discuss many other ternaries here, the freezing this microthermometric response. Okay. So, we will now go on to discuss. So, we have reached a stage, for example, let us say we have selected our sample, got our fluid inclusion sections, have done routine petrography, and we have classified the inclusions, and we have started our work with our aqueous inclusions. There are other inclusions as well. There may be carbonic inclusions and all other types of inclusions. We have taken the data on them. What the microthermometric response for the carbonic fluid will be the discussion for later lectures. And suppose we have generated the data, we have acquired the data on as many number of aqueous inclusions that we have planned initially to take. So, before going on to discuss as to how we present the data, we could possibly quickly discuss some of the issues that might have been there during the course of microthermometry. Generally, it is wise to talk about what are the different sources of error that could be there in our data. The first thing is that calibration, which we have initially during our description of the microthermometric principles as well as the equipment that is used for microthermometric studies. We know that those equipment have to be periodically calibrated for the stability of the equipment, their electronic equipment, and if we have not been careful enough, or there has been some instrumental error where the calibration could possibly have shifted very quickly or very arbitrarily, then there could be a situation in which there could be a source of error. So, this source of error, we can say that it is within the control of our the fluid inclusionist and his instrumentation, and to get the instrument calibrated, if there are some instrumental errors, to rectify those errors, to see to it that the calibration does not shift. And in a system like a Lingam THMSG 600, this is a 3-point calibration that we generally do there. Temperature at a much lower value is corresponding to even -200 or we can go up to -196, when we know that we can make liquid nitrogen to pass through the stage, and one point at about 0, and the another point could be any higher temperature, mostly 500, 600. So, that gives us a calibration line which will be, and then we can go on to take some standards as unknowns. For example, many metal whose melting point is known, and use them as unknowns and can see whether the values are reproducible or not. So, getting an instrument with no calibration problem is the first and foremost requirement for a microthermometric measurement and to make the data meaningful. If the replicate measurements are not done, then as we know that the variation in even 0.1, 0.2 or 0.3 or 0.5 degrees Celsius in the temperature of depression of freezing point would result in difference of 0.3, 0.5 weight percent NaCl, and which will also cause a difference in the density of the fluid. That is not acceptable, that is also not advisable. It is always better to take data which are reliable, accurate and reproducible. The third important aspect of fluid inclusion microthermometry, which needs to be known very well, but little could be done with it, is the metastability. Now, what do we understand by metastability is in the context of occurrence of monophase inclusions, monophase aqueous inclusion, we did mention a little bit about the vapor bubble not actually is being the absence of a vapor bubble in a aqueous inclusion. One of the causes being metastability, means the vapor bubble could not nucleate in the inclusion cavity. That is that can happen, and sometimes the metastability degree of metastability could be feeble to very serious. Sometimes what happens? So, this is one. Number one, that sometimes we get this as the failure of vapor bubble to nucleate, it one. The other is that many times it leads to pretty much consumption of time as well as unsuccessful microthermometric experiments, which sometimes happen, is the lack of response. So, no response on freezing. There is a aqueous biphase, you could see there is an aqueous biphase inclusion. You are subjecting it to the freezing experiment, you see that there is absolutely no change even if you go on decreasing the temperature to -196. Sometimes it is observed. This kind of metastability is sometimes explained that okay, when what we basically wanted to achieve here is that the inclusion to freeze becomes solidified. That does not happen, that is the metastability. Sometimes say it is explained that if there is lack of any kind of a seed crystal or some particle or something that helps in getting the liquid frozen, in absence of that it may not, but that could not be ascribed as a reason in case of fluid inclusions, because when we say that a majority of the cases we get the responses we expect, in some we do not get any response, no shrinkage of vapor bubble, no solidification of the liquid, and it can be only be called that the inclusion is metastable. Even the such kind of exact causes of such metastability is also not very well ascertained. Then sometimes it is observed that the vapor bubble after temperature of homogenization is obtained, the vapor bubble does not come back or fail of reappearance. Exactly, you can say the same as little bit of a variation of the point number 1, the failure of the vapor bubble to nucleate. This is also a metastability. Sometimes this kind of metastability, or you can say that failure of vapor bubble to nucleate or reappear after homogenization. this sometimes can be circumvented by again going on or decreasing the temperature to even far lower value corresponding to again freezing, and sometimes as I said that this metastability, the degree of metastability is variable. Sometimes the metastability is feeble, which can be circumvented or overcome by doing repetitive cycles of such heating freezing experiments, but then the fact remains that only those values which are reproducible should be accepted, or else those values should not be accepted at all. The other one which what we see is the failure in reproducing. Or non reproducibility, you can say that means in a particular single freezing run we determine a temperature of melting of the ice, let us say minus 5.0 degree Celsius. When we are doing a repetitive or replicated measurement, we get values which are completely different, and then completely different value on any subsequent stages of any subsequent freezing run. This also is described as a manifestation of metastability. So, these are some of the points can be discussed as the sources of error, and it is advisable that inclusions which are showing any such problems of metastability, their data should not be included, the data should not be accepted. Only those inclusions where the inclusions respond the way exactly as per our basic knowledge about the phase changes, the phase behavior, and when we get the temperature of homogenization or the temperature of melting of the ice well reproducible, then only we will accept those data, otherwise not. And sometimes it is suggested that the degree of metastability is also related to the size of the inclusion. The inclusions which are generally less than 5 micron size, sometimes even such inclusions display a far greater degree of metastability compared to the inclusions which are of moderately acceptable size range of between 10 to 40 microns or so. But then sometimes it so happens that the sample there could be scarcity of good workable inclusion, and then one has to take measurements on such smaller inclusions, but then the fact is that if those inclusions display such acute degree of metastability, then their data cannot be used. So, we will continue our discussion in the next class and complete the discussion on the aqueous inclusions, and then move over to other topics. So hope to continue in the next class. Thank you.